Hello and welcome everyone to the problem solving session 9. Can anybody please confirm whether I am audible?
Yes, ma'am, you are audible.
Yes, ma'am, you're audible.
Thank you. Thank you. So today's session is on week 9 content. So some multiple choice questions, true or false questions, and some very few numericals based on the content from week 9. So let's see. Okay, so please read this as week 9. So the major content covered in week 9 is on microwave tubes. So it begins with limitations of conventional tubes at microwave ranges, or the need for kind of microwave tubes which we discussed. So professor has discussed on klystron amplifier, then reflex klystron oscillator, magnetron oscillator, and also TWT amplifier. So this is the content covered, and okay, so let's see first just a brief introduction to what are the limitation or for a conventional tube at microwave frequency, or why the vacuum tubes fail at microwave frequency. So some of you can put in chat what do you think, or what do you understood from the video lectures. What are the limitations of a conventional tube when it goes to high frequency? So I'm not seeing any responses. So let me just tell you the very fundamental reason, the very first reason. Yes, as you said, lead inductance. I got a response. Lead inductance and also inter-electrode capacitance. This is one of the major reason. So as you all know, as the frequency increases, this becomes prominent, and this is a serious issue due to which the real part of the input impedance becomes very low, which will short circuit the source and which will reduce the output power. Okay, let's look at another one reason. Is there anything related to transit time effect? So hope you remember what is transit time. So that is a time taken by the electrons to travel from cathode to the grid. So this transit time, or I can denote it like tau or something. It depends on the textbook which you refer to. So tau g or something like that. So if that is, so in case of microwave, that means the frequency is very high. So the time period of the signal or the time period of the wave is very small, which is compared to the transit time. So when that happens, so basically between the cathode and the grid, electron has to transit. But what happens is this polarity of cathode and anode, cathode and the grid keeps oscillating, that means the potential difference keeps alternating several times, due to which the electrons keep oscillating back and forth. Okay, so that is one of the effect of the transit time, and due to which the tube efficiency is very less. Now let me come to the third point. Probably you all know, that is the gain bandwidth product. Gain bandwidth product. So in all conventional tubes, uh, so we get a maximum gain, or we are able to achieve a maximum gain by resonating the circuit. That means we get a maximum gain or a high gain at the expense of a smaller bandwidth. Okay, that is one of the limitation, and this has been overcome. All these kind of limitations have been overcome by the kind of microwave tubes which had been discussed in the video lectures in the week 9. So as I told before, the very fundamental first amplifier which was discussed was a klystron, a two cavity klystron amplifier, and then these two are basically oscillators, in the sense microwave generators. So reflex klystron and a magnetron oscillator. Just one question, do you know what is the kind of oscillator used or a microwave generator used in a microwave oven? Probably you might know. You can type in the chat. What do you think? Yes, that's a magnetron oscillator. Do you know what is the frequency generated? What is it's obviously the microwave frequency, but any guess on what is the frequency? Frequency generated by this microwave oven. Okay, so that is 2.4 gigahertz. Okay, so if you look at the specifications, you might come across this. Okay, that was just something to brush upon. So let us look at some of the questions. While discussing the questions, we can just come across some of the briefing of what is needed. So first question is, lead inductance and parasitic capacitance affect the operation of conventional tubes such as triode in the microwave frequency band. Is it a true or a false statement? Now you all can comment in the chat box, because this has been already been discussed a few minutes back. So hopefully all of you know what it is. You can type in the chat. What do you think? Is it a true or a false statement? Yes, as I am seeing some responses, yes, it is a true statement. Lead inductance and parasitic capacitance is nothing but the inter-electrode capacitance that is going to affect the operation of conventional tubes at microwave frequency. So this is a true statement. Let us go to the next question. Okay, if a conventional tube, okay, please read it as in a conventional tube such as triode operated at microwave frequencies, the transit time of electrons would be small compared to the period of the microwave signal. Even this has been discussed a few minutes back. So hopefully you can comment. Yes, it's a false statement. So whenever you think about microwave signals, yes, its frequency is very high. So the time period of the signal is very, very small compared to the transit time. Okay, so this is a false statement. I hope this is clear. Simple questions basically. Okay, again a true or false question. In a two cavity klystron, the electrons injected from the cathode arrive at the first cavity with uniform velocity. So before going into the question, let me So hope you can see this. So this is a structure of a two cavity klystron. So this is the cathode from which the electrons are emitted, and this is an accelerating anode, and then comes the first cavity. So this is the buncher cavity, and the second is the catcher cavity, and this is a drift space between the cavities. And look at this, this is the collector electrode. So the RF input signal will be applied to this buncher cavity, and the amplified RF output is being taken from this catcher cavity, and the space or the distance, or I can say the length between the two cavities is taken like L. So there is a length between the two cavities. Please note all this because we are going to solve some numericals also based on the two cavity klystron. So hopefully you all know, I am just trying to brush up the concepts. So if you look at this, the principle of operation of this is velocity and current modulation. So as you all know, as the electrons are emitted from the cathode, so it moves with a uniform velocity. It reaches the buncher cavity. So RF signal is being applied here. So based on the RF signals cycle, so whether it is a positive cycle, whether it is a negative cycle, or whether it is a zero crossing, based on that the electron velocity is going to change. So that is your velocity modulation. So because of electron velocity modulation, there is a bunching of the electrons. So that is what is causing and like a current modulation in the catcher cavity, which due to which the kinetic energy which is attained by the electrons will be transferred to this RF signal, which will amplify the RF signal, and the slowed down electrons, so the electrons which lose the kinetic energy are getting slowed down, and those slowed down electrons will be collected by the collector. So this is a very brief, very brief idea of two cavity klystron. So let us now look at the some of the questions. So in a two cavity klystron, the electrons injected from the cathode arrive at the first cavity with uniform velocity. So the question is, I mean, it's a true or false question. So you can comment on this, whether it's a true, what do you think, whether it's true or false. So electrons are just emitted from the cathode and it reaches the first cavity. So is it with a uniform velocity or not? What do you think? Yes, it's a true statement. Electrons reach the first cavity with uniform velocity, and as the RF signal, as it interacts with the RF signal, then it gets it has the velocity modulation. Okay, so let's go to the next question. So the next question is a numerical. So hopefully let me try to just give some basic formula because it's not in the so electron velocity leaving the cathode. So electron velocity leaving the cathode. So it's denoted like V naught 0.593 into 10 power 6 square root of capital V naught. So please note, this is velocity small v naught and capital V naught is the DC voltage applied. Okay, so please note V naught is the DC voltage applied. Okay, then the other thing is gap transit angle. So these had been discussed all in the video lectures. I am just giving the brief. So the gap transit angle theta g can be calculated as omega d by small letter v naught. Okay, so omega is the angular frequency. D, please note, D is the gap spacing, and V naught you already know, that's the electron velocity leaving the cathode. Okay, omega is the angular frequency. Okay, now next is beam coupling coefficient, beam coupling coefficient beta I or beta 1. Some of the textbooks they give it as beta 1. So just write it like sine theta g by 2 divided by theta g by 2. Okay, then DC transit angle, DC transit angle between the cavities, theta naught is equal to omega into T naught. Okay, and this is omega into L by V naught. Please remember, this L, capital L, is the distance between the cavities, the buncher cavity and the catcher cavity. So L is the length or the distance, or I can write it like distance between cavities, and V naught is again the electron velocity. And there is one more equation to tell you, the velocity modulation depth. Velocity modulation depth m is equal to beta 1 into v1 by v naught. So this is beta I basically. V1 is the AC voltage or the RF signal voltage, and V naught, as I told you before, it is the DC voltage applied. Okay, so probably you can take a screenshot of this if you need. So these are some of the brief of equations required to solve the numericals. Okay, let's go to the question. In a two cavity klystron, applied DC voltage is 625 volt. So I can take V naught as 625. Gap spacing in either of the cavities is, so gap spacing is denoted by the letter D, 1 millimeter. If the amplitude of the applied AC voltage, so AC voltage is V1, it is 60. Klystron is operating at 2.4 gigahertz. 2.4 gigahertz. The depth of velocity modulation is, so the question is to find the depth of velocity modulation. Okay, so as we have seen the formula before, velocity modulation depth is given by m is equal to beta I into v1 by v naught. Now we need to calculate what is beta I. How do we calculate that? Beta I is equal to sine theta g by 2 by theta g by 2, where theta g is the gap transit angle, which can be calculated by omega d by v naught. For that we need to know what is the electron velocity. By substituting in this equation, so you substitute the DC voltage here, you can calculate the electron velocity. Okay, so let's start, let's try to solve this sequentially. First you need to calculate the electron velocity leaving the cathode. 0.593 into 10 power 6 into square root of V naught, nothing but the DC voltage. So 0.593 into 10 power 6 into root of 625. Can you please calculate and let me know the answer? So once you get the V naught, what do? You need to calculate theta g. Theta g is omega d by V naught. Omega is 2 pi f. F is 2.4 into 10 power 9 into d is the gap spacing. So 1 millimeter can be written as 10 power minus 3 and whole divided by this V naught what you got here. So hopefully you might have got the V naught as 14.825 into 10 power 6. So if you substitute it here, 14.25 into 10 power 6, you can calculate this theta g. So once you calculate the theta g, you can find what is beta I. Sine theta g by 2 divided by theta g by 2. So the answer, final answer for this beta 1, I am just giving you directly 0.957. Now once you got beta 1 or beta I, then modulation depth. What is the formula for modulation depth? Beta I into V1 by V naught. Beta I into V1 by V naught. So 0.957 into V1 is the AC voltage 60 by V naught is the DC voltage 625. So can anybody let me know what is the answer here? What is the option among the options? Value of theta g. Okay, I am directly giving you beta 1. No need to worry about theta g. You can actually calculate and find that out. Beta 1. If you know beta 1, beta I, you can just substitute directly here and find the final answer for M. Yeah, yes, somebody had responded. Yes, right. So you will get the answer as 0.092. This is the modulation depth. In percentage, it will be 9.2%. Yes, you are right. Okay, I hope this is clear. Any doubts? Or we'll move to the next question. Okay, so the next question is again on a 2-cavity klystron and numerical. So in a 2-cavity klystron, the spacing between the cavities. So spacing between the 2 cavities is given. So that means L. It is denoted by L, and that is 4 centimeters, and the gap spacing in each cavity is, so gap spacing is denoted by the letter D, 1 millimeter. The DC transit angle, so DC transit angle, please remember, DC transit angle is theta naught is equal to omega into T naught, or I can say omega into T is nothing but L by V naught. Okay, so the length divided by velocity, that is T. So okay, so what is so this is given to you, the DC transit angle is given to you, so theta naught is given to you as 40 radian. Okay, and the operating frequency is 2 gigahertz. Okay, if the depth of modulation, so depth of modulation is m, that is 10 percentage, so I can write it as 0.1. The maximum velocity of electrons in meter per second. So the question, please remember, that what is being asked is what is the maximum velocity of electron. Okay, so as the modulation happens, during positive cycle there is a maximum velocity, during negative cycle there is a minimum velocity, and during zero crossing there is no change in velocity. So you are being asked to find the maximum velocity. Okay, so please note this point. We are not asked for the just the velocity of electrons leaving the cathode or something. We are being asked for the maximum velocity of the electrons if the modulation depth is 10%. Okay, so let us see how to solve this. So we can use all formulas which we already know. Theta naught is known to us. Let us write theta naught is 40 is equal to omega is 2 pi f. F is 2 gigahertz, 2 into 10 power 9 into length of the it is a spacing between the two cavities. So spacing between the two cavities is given as 4 centimeter. So I can write it as 0.04 divided by V naught. Okay, now from this you can calculate what is V naught. Can you calculate and let me know what is V naught? So you can try that out. So if you have tried out for V naught, you must be getting 1.25 into 10 power 7 meter per second. So is this the answer for the question? This is the electron velocity leaving the cathode. Okay. So now is this what is being asked? No. If you know that the modulation depth is 10%, you need to calculate the maximum electron velocity. How do we do that? V naught into 1 plus m by 2. Okay, where m is equal to 0.1. Similarly, you can also even calculate V naught minimum. That will be V naught into 1 minus m by 2. Okay, so this is not being asked. So let us see what is being asked. So this is being asked. So if you calculate this, 1.25 into 1 plus 0.1 by 2 whole thing into 10 power 7. So can you let me know what will be the final answer among the options? You can try. I have already given V naught max. Yes. Yeah. So the final answer will be 1.32 into 10 power 7 meter per second. So hope this is clear. If there are any doubts, please ask, or we'll move to the next question. Okay, I think there are no questions. So let me move on. So this is a question on magnetron. So hopefully you remember the structure of a magnetron. So basically in a magnetron you have a cylindrical the basic structure of a cylindrical magnetron is like center you have a cathode, a kind of cylindrical cathode, and then surrounded by that you have anodes which are like cylindrical cavities again. So these anodes are radially placed. Okay, so that is a kind of a structure of a so basically the anode and cathode, and in between you have the cylindrical cavities. So that's a kind of a structure you have for a cylindrical magnetron. So so let us look at the question here. So radii of cathode and anode cylinders are given 5 centimeter and 10 centimeter. So if you have gone through the video lectures, you might have come across these. How do we denote these? So cathode radius is denoted by the letter A, that is 5 centimeter, and radius of anode is denoted by letter B, that is 10 centimeter. Okay, cathode radius and anode radius. E by m, that is E by m ratio, you all know, charge to mass ratio. So E by m is given to you 1.76 into 10 power 11. That is a charge to mass ratio for an electron. Okay. Now if the anode voltage, that means the voltage is given to you, anode voltage V naught is 36 kilovolt. What is the magnitude of Hull cutoff magnetic flux density? Hull cutoff magnetic flux density. So please, I am just going directly to the formula. If you need any details, you can refer to the video lectures. Hull cutoff magnetic flux density B is given by 8 V naught m by E the whole raised to half divided by B into 1 minus A square by B square. So here you can substitute. You know V naught is the anode voltage, E by m ratio you know, and B and A are the radius of the anode and cathode respectively. So just a substitution, 8 into 36 kilovolts, so into 10 power 3. So E by m, so we know E by m, so let me write it like 1 point divided by 1.76 into 10 power 11, and the whole thing raised to half, whole divided by B. B value is 10 centimeters, so I can write it as 0.1 into 1 minus a by b the whole square. So a by b is basically 0.5, 0.5 square. So if you just calculate, simplify this, you will get the answer. Can you try this out and tell me which is the right option? Yeah, right. So the final answer is 17.1 milliweber per meter square. So hope you will get this. All of you can try and see whether you will get the answer. So I hope I can move to the next question.
Excuse me, ma'am.
Yes, please.
Ma'am, I have basically one small doubt.
Okay.
That is not only with respect to magnetron,
Okay.
but also with respect to reflex klystron. These two are basically signal source, signal generators, microwave signal generators. So my question first here, that is for cylindrical magnetron, I understand that the cylindrical structure of the anode, that is going to be the source for the signal generation.
Okay.
So, so based on the Hull cutoff magnetic flux density, that is, the electrons are just grazing that anode and returning back to the cathode, right?
Yes, that's the magnetic field basically. Yeah.
Yes, that is how what makes that to generate the signal there. That is my question. I don't know. I think I'm not clear in explaining. But how the signal, the microwave signal, it starts. That is it.
So your question is, if I decoded it correctly, how the magnetron works?
Yes.
Okay. So basically, magnetron is a cross field device.
Okay.
Where this magnetic field and electric field. So
yes,
these two are perpendicular to each other.
Okay.
So you agree with me on
yes,
that,
yes.
right?
These things.
Yeah.
I am clear, ma'am. But
Yeah.
that how that microwaves are generated from that cylindrical structure. That is.
Okay. So basically, the electric field is radial.
Yes.
And you have the magnetic field. So if you if I have to discuss in detail, I have to explain with all the formulas, derivation and all that. So let me try to make it very simple. Hope you can understand that, or you can go to more explanation in the video lectures. So basically, you know the force, which is V cross B. I mean, force which is basically due to the electric field and due to the magnetic field. So these two forces are there. So, and this will have an angular frequency for this electron's circular motion, that will have an angular frequency. And because of this combined field, I mean the force due to electric field and force due to magnetic field, these two are getting combined here. So because of that, we get a kinetic energy, kind of. So this I can say like two forces create some energy. So energy has to be conserved, right? So this forces which is created due to electric and magnetic field, it is generating the motion. Okay. That is a very brief kind of idea which I can give, but to be specific, I have to discuss a lot.
Yes, ma'am. Now with your explanation, I have conceived some idea.
Okay.
And regarding reflex klystron, that
Okay.
is that we have only single cavity. So
Okay.
the electron beam is passing through the cavity gap, right?
Okay. Okay. Let me try to understand. Reflex klystron has only one cavity. Yes.
Yes.
Ah. So what is your question?
No, that is so there also we are analyzing with respect to the velocity modulation. That is
Yes.
how the velocity is of the electrons are varying
Ah.
with respect to the field in the cavity gap.
Correct. Correct.
But what is the thing is how that initial, because that itself it is a source. So how that initial microwave is generated there. That is my
Oh,
question.
okay, 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 okay. Oh, I understand that. So basically, any oscillator, not just microwave oscillator, we say that any oscillator starts from a very feeble noise signal or something like that, right? And the feedback makes it amplified. So if you think with respect to that perspective also, and please think about the microwave oscillation here, how it has been generated. So basically first the electron beam is injected from the cathode and velocity modulation happens as you already said. And there is a repelling electrode which is making the electrons pass through the gap again. So this kind of an action, so the bunched electrons pass through the gap and this is creating some kind of kinetic energy which is being given to the field inside the cavity. So field inside the cavity could be very very small. So in this process of the electron passing in the gap, the field is just getting built. So that is how finally you get a very good amplified signal. So that's a kind of feedback happening in the oscillator. I can say that.
So the feedback is taking place through the cavity gap.
Not just cavity gap. If you remember the figure of this reflex klystron, you remember there is a repeller. So
Yes.
this repeller electrode will be is having a
Yes,
negative
it will
potential.
turn back towards the source.
Yes,
But
yes. So this repeller electrode is having a negative potential.
yes.
So the electrons are getting repelled and make it pass through the gap several times.
Okay.
So this will create, slowly this will build the field inside the cavity. So I can say that it's a very small field which is getting amplified, and finally you get the RF signal out of that.
Yes. Now it's somewhat clear, madam.
Okay,
Thank,
okay,
thank
okay,
you.
okay.
Hello, ma'am.
Yes, please.
Ma'am, same question is asked in our assignment also, but that 17.1 answer is not there.
Just see the assignment question once again. Maybe some values are changed, or just see that once again. I am not supposed to discuss any of the weekly assignment questions directly.
No, ma'am, it's the same thing.
Okay.
But I have calculated this sum also, but 17.1 answer is not there.
Okay.
Ma'am, could you please check it?
I'll check that. Okay.
Thank you.
Sure. Okay, somebody is giving you a clue. Anode voltage is different. Maybe you can check that. Okay. I don't know who asked the doubt. I hope they have noticed the comment in the chat. So maybe you can check whether the anode voltage is different or not. I am not sure. Please go through the question. Huh? The procedure is this. You can try. So I hope I can go to the next question. It's on TWT, the traveling wave tube amplifier. So hope you remember how the TWT structure is. So it's like a helical structure. Basically it's a slow wave structure. I hope I am not going into the details of that. So the question, let us discuss the question. Diameter of the helix. So diameter of the helix is given. It is 2 centimeters and the pitch of the helix is 2 millimeters. The phase velocity of the wave along the pitch. So the question is to calculate the phase velocity along the pitch. So if you have gone through the lectures, you might have probably come across the equation. Vp is equal to P into C divided by root of P square plus pi D the whole square. Okay. So where P is the pitch, C is the C is nothing but 3 into 10 power 8 meter per second, and D is the diameter of the helix. So you can try this question. 2 into 10 power minus 3 into 3 into 10 power 8 divided by root of P square 2 into 10 power minus 3 the whole square plus pi into D is diameter of the helix, it's 0.02 whole square. I'm not giving the answer. You can try this out and find the answer from the options. So this is a direct substitution of formula for phase velocity is P C by root of P square plus pi D the whole square, where P is the pitch of the helix and D is the diameter of the helix. Anybody could get the answer? Could you find which is the option from here? Yeah, hope you can find it by yourself. Okay, let's go to the next question. A reflex klystron operated in 2 3/4 mode will produce more power as compared to 1 3/4 mode of operation. So in a reflex klystron, you need to look at the dominant mode. So basically the dominant mode is the one which gives more power. So hopefully if you would have listen to the lectures, you already know which is the dominant mode. So can you comment on this question? Is it a true or a false statement? So the idea is should be the dominant mode will have more power. What do you think? Is this a true or a false statement? You can type in the chat. I see no responses. So it's a true statement. Okay. Okay, let me tell you. because I can't discuss the whole thing, but let me tell you in brief. You might have come across n is equal to 2, mode n is equal to 2, or 1 3 by 4. This is the dominant mode, and this will have more power. So you can go back and look at the in detail to the explanation of this. So this uh, 1 3 by 4 will have more power because that's a dominant mode. So this is a false statement. Okay, so any doubts? So thank you all. That's all for the questions which I have come prepared with. So if you have any questions, you can ask them.
Madam, can you please share the screen of first and second question? So that I'll take screenshot. Second question.